Welcome everyone to Reservoir Solutions webinar. It's Abdullah Abdurrahman, a business developer in Reservoir Solutions. Welcome to this webinar. And first, I would like to introduce Reservoir Solutions company and then introduce the speaker for our webinar today. First, for our company profile, Reservoir Solutions is a company that is specialized in providing technical studies and courses for oil and gas companies and professionals. The company incorporates many professionals with diverse technical background related to oil and gas exploration and production. Our services include technical reservoir studies, field development planning, reservoir static and dynamic modeling, economic feasibility studies, technical support for academic researches for PhD and master degrees, assisting in writing technical papers and publishing technical petroleum courses by industry expertise, and we are providing mentorship programs. For our instructor today, Dr. Babak Murati. Dr. Babak Murati is a skilled reservoir engineer with more than 17 years of experience in oil and gas industry. He has successfully led subsurface energy transition projects specializing in carbon and hydrogen storage, enhanced oil recovery, reservoir management and surveillance, and field development planning. Both worked with various international, national, and consultancy companies across different regions, includes UK, Europe, Middle East, Africa, Latin America, and Southeast Asia. His expertise including working with oil and gas, non-operated and operated offshore and onshore sandstone and carbonate assets. He had many roles, including senior reservoir, petroleum engineer, project manager, and energy transition expert in many international companies like Jeffney Callahan, Net Zero Technology Center, Petroxene, and Petronas. He is regular presenter, course instructor, and media releases across multiple topics and disciplines for SPE, EAGE, and IPS conferences. So we would like to welcome Dr. Babak to be speaker for this webinar. At the last, for the webinar rules, if you have any questions, you can ask your questions into the chat box. Also, please mute your microphone and camera in case that you wanted to get a certificate for attendance for this webinar. You can fill into the form that will be sent into the chat box. For upcoming webinars and events, you can join our Telegram, and its link it will be sent into the Zoom chat. You can contact us through the email and the WhatsApp that will be shared also into the chat box. So thank you all, and you can enjoy now the webinar. So Dr. Babak, you can start.
Thank you very much, Abdullah. Can I share my screen? Yes. All right.
Yes.
Perfect. Can you see my screen?
Yes, Dr. Babak, you can start.
All right, perfect. So good morning, good afternoon, good evening, ladies and gentlemen, because I think that we have a broad audience from all over the world. Thank you very much, Abdullah, for the introduction. So today, as you have mentioned, we will go through and we will talk about underground CO2 storage, or CS. So thank you very much. You already presented a biography of myself, so there is no need to do it again. So I will go through the outline of this webinar. So today, first of all, we will talk about energy transition, and we will have an introduction to energy transition. Then after that, we will go through underground carbon storage, and we will have an introduction to that. Then we will talk about geological CO2 storage sites. What are the different types of geological CO2 storage, and what are the options to store CO2 permanently underground? After that, we will go through the estimation and how we can estimate the storage capacity, the CO2 storage capacity. And finally, we will talk about how we can estimate our carbon storage by dynamic simulation. I have an introduction to dynamic simulation to find the carbon storage capacity, injectivity, and other elements that are important in our CO2 storage project. So, as you are aware, currently CO2 concentration in atmosphere has been rising sharply. In year 1750, it was just about 277, but currently in year 2023, it has been risen to 419. It means that it has been increased by 71%. Or from this figure, as you can see, in 1960, the CO2 concentration in atmosphere was just about 318 ppm, but in year 2023, it has increased to 419. This figure, as you can see here, shows us the global fossil CO2 emissions. And as you can see, in year 2022, the global fossil CO2 emissions was about 37.1 plus minus 2 gigatons of CO2, which is 63% higher than in year 1990. Again, in year 2023, we can see that the amount of CO2 emissions from fossil fuels has been increased by about 1.1% and reached to 37.5 plus minus 2 gigatons of CO2. These figures shows us the global map of annual CO2 emissions in year 2021. And as you can see, the China, following by United States, Russia, India, and some oil and gas producers such Iran and Saudi Arabia are the highest emitter in the world. So by having this introduction into CO2 emissions and CO2 concentration into atmosphere, let's see what does energy transition mean. What is energy transition? Energy transition is a pathway toward transformation of the global energy sector from fossil-based to zero carbon by 2050. So the aim is to reduce the CO2 emissions and limit the climate change. So this is the aim of energy transition. And as you know, decarbonization of the energy system, of the energy sector, requires urgent action in all over the world. So we need to take action as soon as possible. Currently, we know that renewable energies and energy efficiencies have the potential to reduce the carbon reduction by about 90%. So we know that our climate has been changed, but what are the key evidence for climate change? How we know that our climate has been changed? We know that the climate is warm. It means that the temperature increased, and we have lots of evidence and lots of indicators from high up to atmosphere to the depths of the oceans. But what are those evidences? The first one is increase in surface, atmospheric, and oceanic temperature. We know that CO2 emissions has raised temperatures even high in the pools. And as a result, we know that the glaciers are rapidly melting, calving off into the sea. So shrinking of the glaciers are another evidence. Another evidence is decreasing snow cover and sea ice. Decreasing snow and ice cover decrease the reflection of the sunlight from the Earth's surface. This increases the amount of light absorbed by the water and land, which increases the regional temperature. Another evidence is rising sea level and increasing atmospheric water vapor. Extra water vapor in the atmosphere falls again as extra rain, which can cause flooding. This evidence we already seen recently. For example, the flooding in Oman, the flooding in Dubai, the flooding in Southeast Asia and other areas. These are the evidence for climate change. So by this introduction, what does net zero mean by 2050? What is net zero? Net zero means that achieving net zero emissions, and means that we need to emit no greenhouse gas by using some, for example, offsets for emissions, or through tree planting, or employing of some technologies like CCS, carbon capture and storage technology. So UK has joined over 120 countries in committing to net zero emissions by 2050, including all G7 nations like Canada, US, Germany, Italy, France, and Japan. So by this introduction to energy transition and net zero, let's see what is CCS. CCS means that carbon dioxide capture and storage, or in other words, CO2 capturing and storing. We have also another term, we call it CCUS, or carbon capture, use, usage, or utilization, and storage as well. So CCS and CCUS, we have these terms for mitigating our climate by capturing the CO2. So CCS is a climate change mitigation technology, as I mentioned before. And the main goal is to reduce the CO2 emissions to the atmosphere. The principle of that is that we are separating and capturing the CO2 from the emitters, from the industry, from the refinery, from the oil and gas wells, and so on. So we are capturing that. Second, we are transporting it. And finally, we are isolating that by storing it into a deep space for storing it safely and permanently. So again, as you can see in this image, we can capture at least 90% of emissions from fixed emitters. Emitters could be, as I mentioned, from industry or from oil and gas and so on, from cement, from power plant, from refinery, from oil and gas wells, and so on. Then we have been transported CO2 for decades. For CCS, we need to also transport it. And finally, we need to store it. This is very important. Safely and permanently underground or in the subsurface by using natural trapping mechanism, which we will talk through them later. Over the past years, there has been a large acceleration of dedicated geological storage development. Total planned storage capacity has more than doubled since January 2022, reaching over 430 megatons of CO2 per year by year 2030. Generally, this provides a positive outlook for CCUS project and signaling strengthened market conditions. Planned storage capacity is catching up with planned capturing. As you can see in year 2022, the orange one shows us the capturing, and the blue one shows us the announced storage. So these are the planned projects for capturing and storing CO2. And that's a good outcome that shows us we are progressing and we are accelerating toward net zero. Again, in this figure, that's a global map that shows us the CO2 emissions clusters from different regions. As I mentioned before, clusters include steel, cement, chemical, power generation, refineries, oil and gas, and so on. As you can see, for example, in North America, we have lots of clusters and also sources of CO2 emissions. In addition, we have lots of potential and planned hubs. As you can see, the green one shows us the potential, and the orange one shows us the planned hub. It means that the planned projects. Or if we go to Middle East or in the UK or in the Europe, we can see lots of opportunities in the North Sea and also lots of planned projects in the North Sea. These figures shows us the global CCS map. This map provides CCS projects around the world. Here we will find information on large-scale projects, operating and planned, which capture, transport, and store at least 500,000 tons of CO2 per year. As you can see from this figure, we have lots of projects, for example, in North America, in Europe, in Southeast Asia, in Australia, and some in Middle East, which some of them are in operation, some of them are pilots, some of them in build, some of them in design, and so on. Next map again shows us the global CCS map. These maps provide about different geological storage type. For example, saline aquifer. We have lots of saline aquifers in Europe. We have some depleted oil and gas reservoirs. We have some projects which are going to implement and store CO2 for EOR purposes, which we will talk through them in next slide to see that what are the geological storage types. So as you can see, in Australia, in Southeast Asia, in Middle East, in the Europe, and also North America, we have lots of operating or in operation or planning projects for different type of geological storage. So let's see what are the geological storage types. What is geological storage mean? This is the first thing, and then we can go to and find what are the main types of geological storage options. First, as I mentioned, geological storage means that carbon dioxide should be captured from industrial processes and it needs to be transported to the storage site. So when we reach to the storage site, we need an injection well to inject the CO2 into the subsurface. So we need some injection wells and inject via a wellbore into a deep geological formation, and CO2 will be in a dense or supercritical fluid, which we will talk about it later. After injection and during injection, we need to monitor the migration of CO2 under buoyancy away from the injection point to see that if the CO2 is, for example, going somewhere else, is leaking. This is very important for us because, as I mentioned, we need to safely and permanently store CO2 underground. So this is very important to monitor that. And we need to ensure the CO2 is permanently trapping. We need some natural trapping mechanism to trap the CO2 permanently and safely underground by, for example, structural or buoyancy trapping mechanism, by dissolution, residual, or geochemical trapping mechanism, which we will talk about them a bit later. So what are the main geological storage options? These are the main options and main types. The first is depleted oil and gas reservoirs. Depleted oil and gas reservoirs means that oil and gas reservoirs which are no longer economic for oil and gas production. So we can repurpose them for CO2 storage. And we have established trapping and storage characteristics because for several years we have produced oil and gas from these wells. or from these fields. So we know that we have seal, we have caprock, we have trapping mechanism here, and we have the storage properties and characteristics to store CO2, to inject CO2 and store it permanently there. The second option is saline aquifer. These are not drinking waters. These are deep saline aquifers. So they are referred to any saline water-bearing formations, and they should have sealed by a caprock for permanent storage. So these are saline aquifer, and mostly their salinity is much more than the sea salinity. Another option is EOR or EGR, enhanced oil recovery or enhanced gas recovery. So we can use CO2 by injecting CO2 into a gas reservoir or a reservoir for producing more oil and gas from mature oil fields. As we have seen in previous slides, there are some of planned projects for EOR in Middle East and in the US. So again, what I mentioned was the main options, but we have also other options as well. For example, the first one, as you can see here, is depleted oil and gas reservoirs. The second was the EOR and using CO2 for enhanced oil recovery. The third one is using CO2 and storing in saline aquifer. The fourth one is using CO2 and storing CO2 in deep unminable cool stems. The fifth one is use of CO2 for enhanced coal bed methane recovery. And the sixth one is other suggested, for example, options like basalts, oil shales, and cavities, and so on. But as I mentioned, the three main options are depleted oil and gas reservoirs, enhanced oil recovery, and saline aquifers. So for any CO2 storage projects, we have 5 main elements for CO2 storage. The first one is the capacity. The second one is injectivity. The third one is monitorability. The fourth one is containment. And the fifth one is the hydrodynamics. So these are the main elements for storing CO2 subsurface. So what does capacity mean? Capacity means how much CO2 can be stored. So this is very important. How much CO2 can be stored in a subsurface, in a depleted oil and gas reservoir, or in saline aquifers, or in other options. Another one is injectivity. How fast can the CO2 be injected? What is the injection rate? How many wells do we need to inject this amount of CO2 in subsurface? The third one, as I mentioned, is monitorability. So what are the best practices to monitor and ensure a safe CO2 storage during and after injection? As I mentioned, this is very important. We want to store CO2 permanently and safely. So monitoring that is very important. There should not be any leakage. If we are injecting into depleted oil and gas reservoirs, for sure, we have lots of legacy or old wells there. So there is a potential and risk of leakage from those wells, which we need to investigate and mitigate that. Containment. What is the risk of CO2 leakage either vertically or laterally? As I mentioned, CO2 can move even vertically or laterally, but we need to be sure that CO2 will be permanently there and will not migrate even vertically or laterally somewhere else. And it will be trapped inside our depleted oil and gas reservoirs or saline aquifer or into our reservoir. And finally, hydrodynamics means that where will the CO2 flow and how will the CO2 plumb evolve? These are another important parameters that are the main elements of CO2 storage. So by having this introduction, let's have a test and quiz, and I will appreciate if you can answer me in the chat box about this question. So What is the ideal minimum depth for storing CO2 in subsurface and underground? 200 200 meter, B, 500 meters, C is 800 meters, and D is 2,500 meters. I will appreciate if you can answer and reply in the chat box and tell me which depth is the minimum depth for storing CO2. What do you think? What is the ideal minimum depth for storing CO2? 200 meter, 500 meter, 800 meter, or 2,500 meter? I will appreciate if you can answer in the chat box. Perfect. Okay. Thank you very much. The answer is C, 800 meters. And why? We will talk about it later. Because when the depth is more than 800 meters and deeper than that, it means that the CO2 is in supercritical condition. We will talk about that later in next slides. So, next question. What is the ideal temperature for storing CO2? The lower the better. A. B, the higher the better. C. Temperature does not affect CO2 storage. So if you can write in the chat box, what is the ideal temperature for storing CO2? The lower the better, the higher the better, or temperature does not affect. Please answer in the chat box. Thank you. Of CO2 into water. And we know that one of the main trapping mechanisms in CO2 storage projects is dissolution. So when the temperature of the site or storage site is lower, it means that more CO2 can be dissolved into water and we can store more CO2. So the lower, the better. We will talk about this again later. So let's go to next question. And next quiz. What is the pressure for CO2? A, 200 psi, B, 1100 psi, C, 500 psi, and D, 10,000 psi. I will appreciate your response in the chat box. What is the ideal minimum pressure for storing CO2? A, 200, B, 1,100, C, 500, and D, 10,000 psi. Okay, thank you very much. So the answer is B, 1,100 psi. And why? Because we need to store CO2 in supercritical condition. And supercritical pressure of CO2 is 1071 psi. So we need to store it more than this pressure. So the correct answer is B, or 1100 psi. So by having this quiz, let's go to our next slide and see what are the key factors that determine a good CCS site, how we can find the best candidate or good candidate for CO2 storage. The first one, as I mentioned, is capacity. So the larger is better. So it means porosity of reservoir rocks need to be more than 10%. Net thickness of greater than 2. Second element is injectivity. Higher permeability means that higher injectivity. So higher injectivity is better. Containment. So we need to have a very good seal integrity. So this is very important as well. Depths between 800 and 2,500. Why 800 meter? To ensure that the maximum of CO2 can be stored in above supercritical condition of CO2. And why it should be less than 2,500? Because deeper than this depth means that the permeability and porosity of the storage will be very low, which are not good for CO2 storage. Than 1,100 psi. Lithology, sandstone is good. We can also store CO2 in carbonate as well. So, question and quiz. Which of following is desirable cap are permeable and act to CO2? A. B. Desirable rock cover a large area and may be porous but low permeability prevents CO2 from entering it. C. Limestones are effective cap rocks. D. Desirable cap rocks cover a large area and have high permeability. Please answer in the chat box. Perfect. Many thanks for your answer. The answer is B. Desirable cap rock cover a large area and may be porous, but they should have low permeability to prevent CO2 from entering it. So, as I mentioned, what are the desired parameter for cap rock? The first one is the lithology. The lithology can be claystone, salt, or halite. The depths based on barrier formation should be higher than 800 meter. Thickness should be more than 20 meter, and as I mentioned, very, very low permeable that could prevent CO2 from migrating and finding a pathway to pass through the caprock. Caprock should seal the CO2 and permanently store it there. So, another question. What happens to CO2 at depths greater than 800 meters? A, it becomes a gas and occupies more space than it would be at the surface. B, it becomes a supercritical fluid and occupies more space than it would be at the surface. C, it becomes a gas and occupies less space than it would be at the surface. D, it becomes a supercritical fluid and occupies less space than it would be at the surface. Please answer in the chat box. Perfect. That's correct. The answer is D. At depths greater than 800 meter, the CO2 will be in supercritical fluid condition and will occupy less space than in the surface. So let's go and talk about that in more detail. So what is supercritical CO2? At standard condition, CO2 is a gas. But when temperature and pressure are increased above the critical point of CO2 is here, is 88 Fahrenheit or about 304 Kelvin. And the pressure of the critical CO2 is 1071 psi or about 7 CO2 condition. So as I mentioned, CO2 at a standard condition, a critical point, it displays properties somewhere between a gas and liquid, and we call it supercritical fluid. Supercritical CO2 is good for injecting because it has a density close to liquid, but a viscosity close to gas. And CO2 density calculate as a function of reservoir temperature and pressure. So what are the change of CO2 density versus depths? As you can see here from this figure, if we consider here as a ground level or sea level, and we go to 800 meters, which is the minimum ideal depth for storing CO2, we can see that the CO2 density is increasing, but its volumes decreasing. As you can see, for example, if we have a volume of 800 meters, depths of 2,500 meters. So it means that supercritical fluid takes up much less space. CO2 has 30 to 40% less density and 5 to 10 times less viscosity than formation brine under typical subsurface condition. CO2 is lighter than the oil, most of the oil, but it is denser than hydrocarbon gases such as methane. So how big is 1 ton of CO2? An adult polar bear weighs approximately about 1 ton. A medium car weighs about 1.2 tons. 1 tons of CO2 at surface occupy about 537 cubic meters. But at the depth of 800 meters, 1 ton of CO2 takes just 1.54 cubic meters. It means that more CO2 can be stored at the depths. So, as I mentioned before, CO2 should be permanently stored by some natural trapping mechanism. What are those trapping mechanisms? We can categorize them into two main groups. First one is physical trapping, and the second one is trapping. And then we can already classify them into structural trapping, residual trapping, solubility or dissolution trapping, and mineral trapping, or we call it mineralization. So these are the main trapping mechanism that can prevent CO2 from migrating to somewhere else, and that can permanently store CO2 underground into our or depleted oil and gas reservoir or our oil and gas reservoir. One of the main important parts, as I mentioned before, we have limitation. We cannot inject by whatever we want. We cannot inject with whatever rate or whatever pressure that we want. The pressure build up must not exceed the fracture pressure reservoirs is the initial pressure of the formation before production. So we can inject until pressure build up and reach to initial reservoir pressure. We cannot exceed that. And the third point is that when we are injecting into saline aquifer, mostly in closed saline aquifers, we need to have some water producer wells as well to mitigate the pressure buildup. So we need to produce the water from those closed or semi-closed saline aquifers. So now we talk about different types of CO2 storage sites and geological storage types. How we can estimate the CO2 and storage capacity, or according to SRMS, we call it storable quantity. How we can estimate the storable quantity? We have two main methods. The first one is volumetric, or sometimes we call it material balance. And the second one is dynamic simulation. But we need to consider that for different type of geological storage, we need to use a different method and different approach. For volumetric estimation of capacity, we have different formula and equation for aquifers, for depleted gas reservoirs, and for depleted oil reservoirs. So we need to use different formula to estimate the capacity when we want to use the volumetric method to estimate the CO2 storage. And also for depleted gas reservoir and for depleted oil reservoir, these equations and formula are different. Another method, which is more reliable, and more accurate is dynamic simulation. In dynamic simulation, when we talk, we need to use some commercial software like Eclipse, CMG, or T-Navigator, and so on. So we have lots of commercial dynamic simulator that we can use them for finding the CO2 capacity and estimate that. But we need to consider that we need to have different, again, keywords when we are, for example, using T-Navigator or Eclipse to find the CO2 capacity in aquifers, in depleted oil reservoirs, or depleted gas reservoirs. So by having this, how we can do dynamic simulation? As I mentioned, we need to have some commercial software like Eclipse, T-Navigator, or CMG, or other simulator, open source, and so on, to estimate that and use it for dynamic simulation. But if we are going to use Eclipse or T-Navigator, as I mentioned, for different application, we need to use different approach and different keywords. For example, if we want to store CO2 into a depleted oil reservoirs, okay? Or for EOR and EGR, we need to use the keyword of CO2 salt. If we are going to store CO2 into a depleted gas reservoirs, we can use the gas vat. If we are going to store the CO2 into saline aquifer, we can use the CO2 store, okay? And in this case, we can have a dissolution of CO2 into water according of water vaporization and salt precipitation. And we can have 3 different phases of gas, water, and solid. If we are going to use it in depleted oil and gas fields, EGR and EOR, in non-saline aquifer, we can use also gas sol keyword as well for dynamic simulation of CO2 storage. So as I mentioned, for different types of geological storage, we need to use different approach. Although we can use some of these keywords for others as well, but we need to consider that if we want to consider dissolution of CO2 into water and also accounting for water vaporization and salt precipitation into saline aquifer, we need to use this keyword. So I hope that you already learned something about this presentation, and thank you very much. And I'm happy if you have any questions.
Thank you, Dr. Babak, for this interesting presentation. I think that some of the participants gained new information about this topic. So again, thank you for your effort and time for explaining the concepts for the CO2 storage. So for participants, if you have any questions, you are free to input your questions into the chat box. Dr. Babak, we have a question about CO2 sequestration into basalt.
Yeah, as I mentioned, one of the options, but this is not the main option for CO2 storage, is storing CO2 into basalts. So because again, we have some pore volumes there that we can store it, but that's rarely used, and that's just under some research projects. As I mentioned, mainly we are repurposing oil and gas reservoirs, saline aquifers, or we can use it for EOR or CO2 storage. Basalts we can find and have some pore volumes, but we need to investigate more and see if they have, as I mentioned, we have 5 main elements, and one of them is containment. Do we have a proper containment, and can we safely and permanently CO2 over there or not?
Okay, thank you. Uh, Also, we have another question about it. Can you tell us some information about how we can measure sealing efficiency in geologic structures?
Yes, this is what we are doing in our dynamic simulation. We are coupling geomechanics with dynamic simulation. By considering geomechanics, now we can find that if our seal is proper for CO2 storage or not. Is there any risk of, for example, having some pathway through the our seal or caprock or not? We can find it by geomechanical studies and coupling that with our dynamic simulation.
Okay, thank you. Another question is saying, you are mentioning into your presentation surface rates. So, how we can measure the surface rates?
That's a very good question. Again, this can be calculated and estimated via some formula or with dynamic simulation. Okay, we can find that, for example, in this storage site, we can store about, for example, 50 megatons. Okay, so in such a case, for example, we are going to inject within 20 years. So in each year, we need to inject about 2.5 megaton per year. So this is our injection rate. But how many wells do we need to inject this amount? This need to be calculated, because as I mentioned, injectivity is the parameter of the reservoir permeability. So there is not one solution for all the geological sites in all over the world. Different reservoirs have different injectivity, have different permeability, and therefore injection rate and number of injectors are different from reservoir to reservoir.
Okay, thank you. We have another question. In saline aquifer, how could we know if the system is closed or semi-closed? It is mostly open system. Is it right?
So this is a good question again. What we need to have a good understanding of the hydrodynamics of those areas. So regional geology is very important. Second thing, we have seismic data that can help us to see that if our aquifers are closed or they are open aquifers.
Okay. Another question. How does injection rate of CO2 and the bottom hole flowing of the injector well affecting the CO2 saturation within the depleted reservoir? He is asking about the effect of the injection rate and the BHP of the injector well on the CO2 saturation in the depleted reservoir.
All right. So as I mentioned, injection rate and injection pressure should be limited. Okay? And for the depleted oil and gas reservoirs, this should not exceed that initial reservoir pressure. So our bottom hole pressure should not exceed initial reservoir pressure in depleted oil and gas reservoir. That should be lower than that. Therefore, when we are injecting, for example, our initial reservoir pressure was 2,000 psi. Okay. Now we are injecting with a rate, and our bottom hole pressure constraint should be lower than 2,000 psi. Therefore, we will not exceed the initial reservoir pressure, and in saline because they are not depleted. So they have the same pressure as, for example, have years ago or to produce from them. In open aquifers, there is no issue. The pressure buildup is not an issue. But in closed system, yes, the pressure will build up, and the pressure should not exceed the fracturing of the seal. If there is a risk that the pressure can be higher than the fracturing of the seal, we need to add some water producer to decrease the buildup pressure.
Another question is asking about what the best for CO2 storage in terms of lithology, carbonate or sandstone or whatever.
Yeah, that's a very good question. We know that carbonates are more heterogeneous, and we also, some of them are fractured. So the answer is sandstone is better, but we have lots of potential of carbonate reservoirs in Middle East and other part of the world. So we need to consider them as well. Okay. In such a case, what we are doing, we need to screen and then rank. For example, we have 10 different depleted oil and gas reservoirs and an aquifer. Okay. In such a case, we need to screen and find if they are proper for CO2 storage or not. We need to find and assess and evaluate our risk. One of our risk carbonate reservoirs. So if we have a large network of fracture, that should be or that can be some risk of CO2 leakage to other layers that we need to investigate or mitigate them before injection. So in such a case, for example, we found that we have a fracture in that area. So we need to drill our CO2 injector far away from those fractured and fractured networks to avoid pathway and migrating of CO2 into other areas.
Okay. Another question, he is asking about the formation of CO2 hydrates. Is that helping into storage of CO2?
Can you say again the question?
Okay.
CO2 what?
He is asking about if the formation of CO2 hydrates helping in the storage of CO2.
Yes, there is a risk of that. Hydrate can be happened in CO2 storage projects as well. And this is one of the risks that we need to consider it, because hydrate is mainly affected by temperature. So for example, if we are in a very low temperature area and winter can affect us, hydrate can be one of the uncertainties and risk, and we need to mitigate. We are injecting MEG with our CO2 to prevent the hydrate formation.
Another question he is asking about, how about injecting into deep oceans for storage?
If you are injecting oceans, okay, because there is not a seal, there is not a cap rock. So CO2 rate, although, for example, that will take some times, but it will reach to the surface, maybe after 50 years, 100 years, and so on. So the best methods is to store it in a subsurface when we have a seal to store it permanently there.
So I want to apologize for your for you, Dr. Babak, because we are receiving a lot of questions. So sorry for your time.
And no problem. They can already email me,
Okay.
or uh, they can ask me via LinkedIn. I'm available to talk more about that if needed.
Just one last question. What about the cap rock sealing efficiency? And how much CO2 can we store in a depleted reservoir, avoiding the leakage of the cap rock?
So in a depleted oil and gas, so this is what we are aware. Some gas or some oil are still locked. For example, this number, we can see that the maximum storable capacity of this field can be via this formula, as I mentioned to you. Initial gas in place minus what is remained in the reservoir. This is the highest amount that we can inject CO2 by considering CO2 properties as well, okay? But as I mentioned, we have some reservoir pressure. So the best way to find that is by dynamic simulation. But when we are doing, for example, some volumetric or material balance equation, we need to just consider what I mentioned too: the initial gas in place, the remaining gas in place, and then consider the density of CO2 and what the reservoir will be reached to, for example, after that calculate the CO2 capacity. But in dynamic simulation, we can have a better prospect and find more detail about that, because in dynamic simulation, we are already considering different trapping mechanism. We are considering the dissolution, we are considering, for example, the residual trapping, we are considering what can be stored via structural trapping. Mineralization is a long-term, required 1,000, for example, years. So sometimes we do not consider it, but those trapping mechanisms have a better answer to this question, that how much CO2 can be stored and what will be the best or optimum pressure and injection rate for storing more CO2 into the reservoir. So as I mentioned, our constraint is initial, and maximum capacity that we can store is the difference between initial gas in place and the remaining gas in place in the system.
Okay, thank you, Dr. Babak. So I think that will be the end for our webinar. So at the end, at behalf of Reservoir Solutions team, I would like to thank Dr. Babak Muradi for his sincere effort and time to deliver such interesting webinar that we think that all the participants gain a new information about underground CO2 storage CCS. Also, I would like to thank
Thank you
you.
very much, Abdullah, for organizing this webinar.
Thank you, Dr. Babak, for your time and effort for this webinar.
Yep. Cheers. Thank you. Have a good day.
Thank you. Thank you.
Bye.
Have a good day too, Chairman. Also, I would like to thank all the participants for their time attending for this webinar, and I would like to remind them, if you want to have a certificate for attendance for this webinar, you can fill into the form that will be sent into the Zoom chat. I will send it again today now. Okay, so you can find it into the Zoom chat. Also, I would like to remind them, if you would like to enroll into the next events for Reservoir Solutions, you can join our Telegram channel or subscribe to our YouTube channel, where you can follow our LinkedIn page to be updated about the next events in chat. So we have 5 minutes, then this webinar, it will be closed. If you miss anything, any information about this webinar, you still can catch it into our YouTube channel. Okay, so the recording, it will be shared into our YouTube channel. Thank you all. Have a good time and Assalamu alaikum.
Thank you very much. Wa alaikum salam.